Here are the key conventions to employ. 1. Disfluencies and fillers. Generously use words like, well, and so these shouldn't just be the beginning of sentences, but scattered naturally within clauses. Example. It's really about how you scale the system. 2. Back-channeling and acknowledgments. The non-speaking person doesn't just sit in silence. They interject with short agreements or reactions like, right, yeah, exactly, wow, or example, host speaker. And they found a perfectly straight line on the graph, expert speaker. Right. Host speaker, which is just wild for empirical science. 3. Interruptions and overlaps. Use double dashes to indicate someone cutting in, trailing off, or restarting a thought. Do not use ellipses. Example, expert speaker. The problem with that is host speaker, the cost. Expert speaker, exactly. The cost is just astronomical. 4. Colloquialisms and casual phrasing. Use contractions heavily. It's there. Couldn't. And conversational idioms suitable for a technical but relaxed audience. Crank up, burn compute, under the hood. 5. Pacing. Break up complex explanations. If one speaker has a long technical point, the other should jump in to confirm understanding, ask for clarification, or just react. No single turn should feel like a textbook paragraph.
Okay. So when you look at the actual server costs,
Oh, they're terrifying.
right? I mean, you're just burning cash at that point.
Yeah, and that's why, the baseline ratio isn't always the right move for production.
Wait, really? Because I thought that was the absolute golden rule.
Yeah.
Natural notes. Imagine spending like $100 million to build a massive supercomputer cluster.
Right, just a casual infrastructure bill.
Yeah, exactly. You rack tens of thousands of GPUs, you wire up all the networking, you finally hit the execute command on your training run, and, you have absolutely no idea if the final output will actually work.
It was terrifying. I mean, for years, that was the actual reality of training artificial intelligence. It was a wildly expensive roll of the dice.
Because if you're building a traditional microservice or, just a standard CRU'd app, you have deterministic behavior.
Exactly. You write the logic, and if it fails, you get a stack trace, you find the bug, you fix it.
But machine learning was closer to alchemy. You'd stir the pot, tweak a learning rate, add some layers, and just pray the loss function went down.
And if it didn't go down, you rarely knew exactly why. You just had to guess and run the whole experiment again.
Yep.
So welcome to the deep dives. Tonight, we are unpacking the mathematical breakthroughs that took AI from that dark art of alchemy and turned it into a precise, highly predictable engineering discipline. We are talking about scaling laws.
It's such a massive shift.
It really is. And for you, the software engineer listening, the one actually integrating these models, building the wrappers, or footing the AWS bills, understanding these laws isn't just academic.
No, not at all.
These are the absolute, unyielding rules of physics that dictate the billion-dollar architectural decisions shaping every single API you use today.
Yeah, and to really understand where we are right now, you have to look back at the paradigm shift that happened in 2020.
Right, the turning point.
Exactly. Because up until that point, the entire machine learning community was basically fumbling in the dark. You had all these teams trying wildly different architectures, just, trying to figure out what actually mattered.
Throwing things at the wall.
Pretty much. But then a team at OpenAI, led by Jared Kaplan, published a paper that completely rewired the industry's brain.
The Kaplan paper.
Yeah. They decided to systematically study how a model's loss behaves when you change the physical scale of the training.
And just to ground that for a second, loss is basically the mathematical measure of how wrong the model's predictions are, right? So the lower the loss, the better the model is at predicting the next token.
Precisely. So the Kaplan team, they isolated 3 specific levers of scale. First, the number of parameters.
Which is the sheer size of the neural network.
Right. Second, the data set size, which we measure in tokens. And third, the total compute budget used for the training run, usually measured in FLOPs or floating point operations.
Okay, so parameters, tokens, FLOPs.
Exactly. And they ran this massive series of experiments just plotting the loss as they cranked up those variables.
And what they found is the kind of thing that makes physicists and engineers just jump out of their chairs.
Oh, absolutely. They found a smooth, perfectly predictable power law.
Wow.
Yeah, if you plot the relationship between the scale of the model and the loss on a log graph, meaning, both the x and y axes increase by orders of magnitude, the data points form a dead straight line.
A straight line. In machine learning.
Right. It wasn't noisy, it wasn't chaotic, it was mathematical certainty.
Let's unpack the mechanics of that power law, because a straight line on a log-log graph means you're dealing with compounding fractional improvements.
Exactly.
So the math Kaplan uncovered showed that if you have a power law exponent of roughly negative 0.076 for your parameter count, doubling the size of your model predictably drops the loss by about 5%.
And, at first glance, a 5% drop for literally doubling your compute footprint, that sounds like a terrible deal.
It sounds like brutal diminishing returns. Like, why would I pay twice as much for 5%?
Right. But the magic is in the compounding over massive scales.
Ah,
If you don't just double the parameters, but scale them up by a factor of 100, say, going from a 1 billion parameter model to a 100 billion parameter model, that 5% drop compounds into a massive transformative leap in the model's fundamental capability.
and the truly crazy part to me is that because the curve is a straight line, you can calculate the exact performance of a 100 billion parameter model while you were only running a tiny, like 10 million parameter test model.
Yes, that is the exact moment alchemy became engineering.
Wow.
You could predict the final intelligence of the system before you ever signed the purchase order for the GPUs.
Which is huge for the folks writing those checks.
Oh, completely. And because the math was so clear, the Kaplan paper came with a very specific blueprint for how to build the future.
Okay, what was the blueprint?
They looked at the curves and concluded that if you have a constrained compute budget, which, everyone does, you get the best return on investment by aggressively scaling the parameter count first.
So build the biggest model possible, even if you don't have enough data to train it for very long.
That was the playbook. Pour your FLOPs into making a massive neural network. And that philosophy is the direct reason GPT-3 looked the way it did in 2020.
Right.
OpenAI built a towering behemoth, 175 billion parameters, but they only trained it on about 300 billion tokens of data.
It's kind of like a bottomless swimming pool.
How do you mean?
Well, before this, conventional wisdom assumed there was a hard ceiling on how much a neural network could actually absorb, right?
Yeah.
People thought if you made it too big, it would just memorize the training data and fail to generalize.
Oh, right, overfitting.
Exactly.
Huh.
But Kaplan basically proved the pool is effectively bottomless. Every bucket of parameters you pour in raises the water level predictably. So the industry just started building the widest pools they possibly could. We entered this era of massive towering models.
We did, but the strategy of just building wider pools didn't last very long. No, just 2 years later, the entire industry violently pivoted away from Kaplan's specific recipe.
Oh, right, because DeepMind dropped the chinchilla paper in 2022 and completely rewrote the rulebook.
Yeah, they really did.
If Kaplan gave us the power law, DeepMind gave us the exact golden ratio.
That's a great way to put it. The chinchilla research team suspected that the industry was actually misallocating its compute.
Interesting.
So to prove it, they executed an incredibly rigorous mapping of the loss landscape. They didn't just train a few models, they trained over 400 different models.
400.
Yeah, ranging from 70 million parameters all the way up to 16 billion. And they systematically varied the ratio of parameters to training data, looking for the absolute most efficient way to spend a given compute budget.
And the revelation from that was just a massive reality check.
Yeah.
Because it turned out the entire industry was radically undertraining its models.
Completely starving them. They found what's called the compute optimal frontier. DeepMind mathematically proved that to get the lowest possible loss for your compute, you need to scale your model size and your dataset size in equal proportions.
Okay.
Specifically, they discovered what is now famously known as the chinchilla ratio.
Right, the magic number.
Yep. For every single parameter in your neural network, you need to feed it about 20 tokens of training data.
Which means the reigning champion of the time, GPT-3, was essentially a giant running on fumes.
Exactly.
Because it had 175 billion parameters, but only saw 300 billion tokens. That is a ratio of roughly, 1.7 tokens per parameter?
Yeah, not even close to 20.
To hit the chinchilla optimal frontier, a model that size should have been trained on 3.5 trillion tokens.
It was starved.
Starved is the perfect word for it. And DeepMind proved this point by putting it into production. They built a model called Chinchilla, gave it 70 billion parameters.
Which made it less than half the size of their previous flagship model, Gopher, right? Exactly. Less than half the size. But they fed it 1.4 trillion tokens, adhering perfectly to that 20-to-1 ratio.
So it's like the athlete's training regimen.
Yeah.
Like Kaplan's math convinced the industry that the only way to win the Olympics was to build a physically larger athlete. So we got these towering 175 billion parameter giants.
Right.
But DeepMind looked at the tape and realized, hey, the giant is massive, but malnourished. They proved that if you take a smaller athlete and feed them a massive high-calorie diet of data, they will just run in circles around the starving giant.
And chinchilla did exactly that. It completely swept the benchmarks.
Wow.
It fundamentally shifted how engineering teams thought about resource allocation. Suddenly, data was just as important as parameter count.
Wait, hold on, though. This is where the software engineer in me have to look at the reality of deploying this stuff.
Okay, let's hear it.
Because chinchilla optimizes for the absolute lowest loss during the training phase.
Right.
But as an engineer building an application, training is a one-time CapEx. It's a sunk cost. Inference, actually serving that model to millions of users, holding those weights in GPU memory, generating tokens day after day, that is an infinite OpEx.
Yep. The meter's always running.
Exactly. Doesn't the sheer cost of server bills mean we should completely ignore the 20-to-1 rule in practice? Shouldn't we intentionally overtrain much smaller models just to keep our inference latency and VRAM footprint manageable?
You've just described the exact architectural philosophy driving the current open-source AI ecosystem.
Oh, really?
Yeah, the chinchilla ratio is merely the baseline now. It tells you the minimum viable data required to justify a model size.
Okay.
But when you factor in the lifecycle cost of serving that model at scale, the math flips. You willingly burn more compute upfront during training to shrink the final deliverable.
Because serving a 175 billion parameter model requires stringing multiple A100 GPUs together just to hold the weights in memory before you even process a single user's prompt.
Exactly. A smaller model saves millions in infrastructure. Just look at the evolution of Meta's open weights models.
Right, the Llama series.
Yeah, the original Llama model had 65 billion parameters and was trained on 1.4 trillion tokens.
So that's a ratio of about 21.5,
Yeah.
almost perfectly aligned with the chinchilla optimal ratio.
Exactly. But when they released Llama 2, the strategy changed. They kept the size roughly the same at 70 billion parameters, but they trained it on 2 trillion tokens.
Pushing the ratio to nearly 29-to-1.
Yep.
So they deliberately blew past the compute optimal frontier. They spent the extra FLOPs in the data center so the developers could run a highly capable model on cheaper hardware.
Exactly. The current meta is absolute brute force overtraining. But doing that introduces a terrifying physical bottleneck.
The data wall.
Yes.
Because if the new engineering standard is taking a right-sized model and force-feeding it disproportionate amounts of data to save on inference costs, you run out of food very quickly.
Very quickly. Let's do the math on it. If you want to build a true next-generation model, say 1 trillion parameters, and you just want to hit the baseline 20-to-1 chinchilla ratio, you need 20 trillion tokens of data.
And if you want to overtrain it for inference efficiency, like Llama 2, you might need 30 or 40 trillion tokens.
Right. And here's the bottleneck. Data scientists estimate that the entire high-quality, publicly available internet, we're talking Wikipedia, published papers, news articles, Reddit, GitHub.
Basically everything.
Yeah, all of it. It only contains somewhere between 5 and 15 trillion tokens.
Wow.
We are literally exhausting the digital exhaust of human civilization.
So are we basically trying to build an infinitely scalable steel factory, but waking up to the reality that we've already mined all the raw iron ore on the planet?
That is exactly the crisis keeping AI labs awake at night right now.
But can't they just use more of the internet?
Well, you can't just scrape low-quality SEO spam. Bad data actively harms the model's performance.
Oh, right. Garbage in, garbage out.
Exactly. So engineering teams are deploying aggressive, highly sophisticated deduplication pipelines to squeeze every single drop of signal out of existing data sets.
Makes sense.
They're locking down massive licensing deals for paywalled corporate archives and books, but fundamentally they're pivoting to multimodal architectures.
Because video is like a cheat code for data density.
Precisely.
A page of text might be a few hundred tokens, but a single minute of high-definition video contains thousands of frames, complex physics, object permanence, lighting, spatial reasoning, audio. It is just this ocean of implicit world knowledge.
Video is the lifeboat. Multimodal is how we keep scaling. And the other workaround is synthetic data.
Using AI to train AI.
Yeah, using an existing frontier model to generate highly complex curated data to train the next generation of models.
So how viable is that really? Like if the models start training on their own synthetic output, don't they just start eating their own exhaust?
Right, the model collapse problem.
Yeah, we've all seen the research on model collapse, where a model trained on AI-generated data slowly loses the fringes of its knowledge distribution and just collapses into a generic repetitive mess.
Yeah, model collapse is a severe mathematically proven risk if you just blindly feed a model its own generic output.
So how do they avoid that?
The nuance is in using synthetic data as a filtering or reasoning mechanism.
What do you mean?
Well, you don't ask the AI to write a novel and train on it. You ask a massive model to generate millions of complex coding problems, and then you use a traditional compiler to verify which solutions actually compile and run.
Oh, wow.
And then you train the smaller model only on the mathematically proven successes. You are using compute to manufacture high-signal data.
That's incredibly clever.
It is. But even with these tricks, the data wall is the most pressing physical limit on the scaling laws right now.
Let's pivot from the limits of training back to what these models actually feel like to use. Because we've spent this entire time talking about the loss curve smoothly decreasing on a log graph.
Right.
But smooth math under the hood produces what looks like sudden jarring magic on the surface.
Ah, you are touching on the phenomenon of emergent abilities.
Yes.
This is where the engineering of scaling laws collides with the philosophy of intelligence. Back in 2022, researchers started documenting this really bizarre pattern.
What were they seeing?
They would test models of various sizes on complex tasks like multi-step logic puzzles or translating proverbs between obscure languages.
And the results were incredibly discontinuous. Like, you test
Yeah.
a 1 billion parameter model, and it scores 0%, just guessing randomly.
Yep.
You test a 10 billion parameter model, still 0%. The line's completely flat. But then you scale the parameters up to 100 billion, and suddenly, vertically, the accuracy shoots up to 60%.
Right. The underlying math of the model, the loss, is improving smoothly the entire time, but the actual capability seems to just switch on overnight.
It's so weird.
It's like lowering the temperature of water. You go from 10 degrees to 5 degrees to 1 degree. The water is smoothly cooling, but its physical state remains liquid. The moment you hit exactly 0 degrees, the entire system abruptly undergoes a phase transition and freezes into solid ice. That is what emergence feels like.
Wow.
It suggested that scaling up didn't just make models better at what they already did, it spontaneously unlocked entirely new cognitive skills.
I have to challenge that magic from a pure software testing perspective, though.
Go for it.
As developers, we know that binary exact match tests are notorious for hiding continuous underlying progress.
Okay, true.
Right. If you ask a model to write a 10-line Python script, and it gets 9 lines perfectly right but misses one single indentation, the script crashes.
Yep, it fails.
The exact match score is 0%. But if the larger model gets that final line right, the score jumps to 100%. Doesn't the illusion of a sudden jump just come from how brutally binary our metrics are?
That exact skepticism sparked a massive debate in 2023. Researchers actually went back and looked at those exact same emergent tasks.
And what did they find?
Well, instead of using a binary pass-fail metric, they measured the continuous probability, the log likelihood that the model was assigning to the correct answer.
Okay, so it's like the widening gap analogy.
How so?
Imagine a track and field athlete training to jump across a 10-foot chasm. Every week of training, their leg muscles get 5% stronger. That is a smooth, continuous curve.
Right.
But if your only metric for success is, did they make it to the other side of the 10-foot gap, their score is going to be 0% for months.
They keep falling in.
Exactly.
Yeah.
But the day their continuous leg strength finally allows a 10-foot jump, their success rate goes from 0 to 100 instantly. The capability was continuously growing, but the binary threshold made it look like sudden magic.
The 2023 research proved exactly that. When you look at the continuous probabilities, the model is smoothly, incrementally figuring out the task as it scales. The sudden phase transition is largely an artifact of the exact match metric.
Interesting.
However, for the engineer actually deploying the API, the philosophical distinction doesn't really matter.
That's true.
Whether the underlying capability is continuous or not, the product reality is that small models cannot do the task, and massive models can. The utility truly does emerge at scale.
And because that utility unlocks so predictably, the industry has locked itself into the most brutal, game-theoretic compute arms race in the history of silicon.
Oh, without a doubt, the sheer velocity of the escalation is difficult to even comprehend.
Give me some numbers.
Well, in 2019, training GPT-2 took roughly 1.5 petaflop days of compute.
Okay.
Just a year later, GPT-3 required around 3,600 petaflop days.
That is a massive jump.
And by the time GPT-4 finished training, estimates suggest it consumed somewhere between 10,000 and 100,000 petaflop days.
Unbelievable.
We are talking about entire data centers drawing enough power to run a small city, doing literally nothing but matrix multiplication for months on end. Every single generation requires orders of magnitude more capital.
All driven by the scaling hypothesis.
This is the deeply held, almost religious conviction among top AI labs that we don't need to invent a fundamental new paradigm to achieve artificial general intelligence.
Right.
The belief is that the standard transformer architecture, combined with the Kaplan and Chinchilla scaling laws, is all you need.
Mm.
You just need a bigger data center, more power, and more tokens.
The proponents of the scaling hypothesis look at that log graph and say, the line hasn't bent yet. Keep buying GPUs.
Right. But there are skeptics, too.
Oh, definitely.
Yeah.
The skeptics look at the exact same line and see a fundamentally limited statistical trick. They argue that driving the loss function down just creates a more sophisticated mimic. It memorizes broader patterns, but it isn't truly reasoning. It doesn't have an internal world model.
But the reason the scaling hypothesis commands billions of dollars is its terrifying universality.
Yeah, it's everywhere.
These power laws aren't just for natural language. They govern computer vision models. They map perfectly onto reinforcement learning for robotics. And for the software engineers listening, scaling laws are most aggressively visible in code generation. Because syntax is unforgiving. A missing bracket breaks the build. To achieve the syntactic precision required to generate complex working architecture, you need a sheer probabilistic weight that only massive scale provides. The math is universal.
Which means the arms race is completely rational behavior.
Wow, yeah.
If you're a tech CEO and you know mathematically that spending 10x more on compute will yield a predictably smarter model that will cannibalize your competitor's product, you have no choice but to sign the check.
You have to do it.
The power laws dictate that the cutting edge of human technology is now bottlenecked purely by access to capital and electricity.
That is a wild place to be. We've covered a massive amount of ground today. We started in the era of alchemy, just fumbling in the dark.
Seems like a lifetime ago.
Right. Then we watched the Kaplan paper reveal the hidden geometry of the power laws, birthing the massive parameter giants.
Yeah.
We saw the Chinchilla ratio violently correct the course, proving that data starvation was holding the industry back. We navigated the harsh reality of inference cost trade-offs, stared down the looming data wall, unpacked the illusion of emergent abilities, and arrived at the multi-billion-dollar bet on the scaling hypothesis.
The rules of the game have been mathematically mapped.
But I want to leave you with one final thought as you go back to building with these APIs. The scaling laws prove there is no hard ceiling, but physics and economics enforce brutal diminishing returns.
Very brutal.
Getting a model from 90% accuracy to 95% takes a staggering amount of compute, but pushing it from 95% to 97.5%, you have to multiply your massive compute budget by 10 all over again just to get that tiny fractional gain.
It's exponential cost for linear gain.
Exactly. At some point, the brute force scaling curve becomes too expensive for even the trillion-dollar tech giants to sustain. When the brute force fuel runs out, what happens next?
That's the billion-dollar question.
Will the next era of AI be defined by whoever can secure the most nuclear power plants? Or will it require an engineer's cleverness architectural shifts, like mixture of experts or state space models, to fundamentally bend the curve and break the laws altogether? Because if the history of AI has taught us anything, it's that yesterday's alchemy is just waiting for today's engineering. Thanks for diving deep with us. Keep building.